To kind of start and assess this idea of conservation of energy, I want to touch back on last week's module on momentum. And we talked about essentially 3 different collision types. When 2 or more particles collide with each other, it can be in a perfectly elastic collision, it can be in an inelastic collision, and then it can be in a perfectly inelastic collision. And to some extent, the difference between those is just the amount of energy that is lost. In perfectly elastic collisions, no amount of energy is lost. So we have seen before, so if I had the 2 particles, I could have one particle, we'll call this A, and it's traveling to the right with some initial velocity, we'll call that the initial velocity of A. And particle B is coming from the other direction and it's traveling towards A. This is the initial velocity of B. When they collide, we know from momentum that the momentum before, so the momentum of A plus the momentum of B, this would be the initial or before the collision, should be equal to the momentum after. This would be A final plus B final, sorry. B final. And in terms of that, that's just their mass and respective velocities. The mass of A, the initial velocity of A, plus the mass of B, the initial velocity of B, that's going to equal the mass of A, the final velocity of A, plus the mass of B, the final velocity of B. Okay, and in any type of collision, we've looked at the conservation of momentum, where we're going to add kind of this little additional piece of information is looking at what happens when energy is also conserved in this system. And we can kind of think of that as we've just learned or previously looked at in the lecture notes, the equation for, and this specifically we're going to be talking about kinetic energy for the context of collisions that we're going to be looking at. The kinetic energy is conserved. The kinetic energy equation I represent as KE. Sometimes you'll see it written just as capital K. This is equal to 1/2 mv squared. You'll notice, so the 2 subtle differences here. This is actually very similar to the momentum equation. You see a mass and you see a velocity in there. You see a mass and you see velocity squared. In fact, actually, the relationship is the kinetic energy is the integral, the velocity integral of momentum. If you're not understanding that from a calculus base, you can think of it as the area under the curve of a momentum versus velocity graph. Now, so there's a very strong relationship between them there. The very big difference I wanted to note, though, is for momentum, velocity is a vector and it's not being squared or anything is happening to it. So it stays, momentum is still a vector. It stays a vector. This velocity component in kinetic energy is now being squared, which essentially takes the vector and makes it a magnitude. So it's now effectively a scalar. So its direction is irrelevant. It's always going to be positive. We can't have negative kinetic energy. That doesn't denote it's moving backwards or anything like that. Kinetic energy is always going to be some positive quantity. But in order for this to be perfectly elastic, I would essentially be saying the kinetic energy, just like we set up for the momentum, the kinetic energy of A initial plus the kinetic energy of B initial. And both of these would be some positive number if they were both moving. It doesn't matter that B is going in the negative direction. Their combined energies would be equal to some kinetic energy of A final, whatever it is. If it changes, it's going to be based on how its velocity changes, plus the kinetic energy of B final. And that's going to look like 1/2 the mass of A, the initial velocity of A squared, plus 1/2 the mass of B, the initial velocity of B squared. And that's going to equal 1/2. You see where I'm going with this? A final velocity of A squared plus 1/2 mB, the final velocity of B squared. And I think I got all my letters right. Got to check all those. So to essentially assess when these conditions are both met, we can look at a few different scenarios or examples. And the first thing I want to do is actually want to set up and show you the example that we looked at from last week's lab when we looked at collisions. So we can take a look at, again, that introductory collision lab. we're not going to do the exploring 1D motion. We're just going to look at the intro for this case and purpose. And we had set up a few previous examples where for this case, I have the initial mass of the first ball. So in this case, it's a blue ball. Going to the right, it has a specific velocity. I'm going to actually check the values here so we can see what's exactly going on here. Its initial velocity is 1 meter per second. Going to the right, it already immediately calculates its momentum based off its mass and initial velocity. The mass of the second ball is 3 times the mass of the first. It's 1.5 kilograms, and it's half the velocity going to the left. And I can play, so in terms of this case, the system or the simulator will automatically set up a perfectly elastic collision. We'll notice the elasticity is set to 100%. It calculates the kinetic energy going into the system. So if the energy is conserved and momentum is conserved, so the momentum going into the system, I can write as the net momentum between the two. That'd be the 0.5 kilograms minus 0.75 kilograms. So we'd have a net momentum of negative 0.25 kilograms. The negative denotes my net momentum is to the left because the second mass is bigger, right? So it's going to have an overall net momentum to the left. So that same momentum should be the same after the simulator, after they collide. The kinetic energy should stay the exact same. So if I run the simulator, that's exactly what I see. I see the kinetic energy has not changed at all. If I take the difference between the 0.63 and 0.38, I get exactly negative 0.25. So momentum's conserved, kinetic energy is conserved. And you can think, well, this is what we saw last week. Fairly useful, very straightforward. But using the two conservation equations or principles, we can actually set up systems where we can tell when is the system going to meet the criteria of being perfectly elastic. Essentially, when is energy and momentum both being conserved? Just to kind of make this make a little more sense, I'm going to do this in maybe a different color here because there's a lot and this gets kind of messy. We're essentially going to set these equations, and I'm just really specifically doing this one and this one. We're going to solve both of these equations for the way I have it is solving for the final velocity of the first ball. And then I'm going to use a Desmos file for us to kind of set it up because these get kind of messy. It's kind of tricky. But essentially what this is going to be, so from the first equation, this one right up here, and I'm going to copy paste it because I can. We can set the momentum equation, we can set and solve for this final velocity of A. So if I subtract this to the left side, and then I divide everything from the mass of A, I get essentially that the initial velocity of A plus the mass of B over the mass of A times the initial velocity of B minus the final velocity of B is my expression for solving for, and again, this is solving for the final velocity of A. I should have put that on there. Solving for the final velocity of A. Now I did that pretty quickly. You can check it after, you can pause it and try and solve for yourself, but I'm just setting the equation equal to just this term right here because that expression holds true. So that's coming from our conservation of momentum. Conservation of energy also needs to hold as well. So I'm going to take the conservation of energy equation to create my second equation. And this is going to, all the 1/2 terms cancel out. The way I'm setting it up here, don't think that you can always cancel the 1/2 term out. The way I'm doing it this way can cancel out. If I move and manipulate, I get that the final velocity of A is equal to the square root. This then becomes the initial velocity of A squared plus mass of B over mass of A. Again, I'm doing this kind of quick, but V initial of B squared minus V final of B squared. And these two now can be kind of tricky to set and solve for in one fluid equation. What I like to do is use another acceptable method for solving a system of equations. In fact, your algebra days is graphs. Where the graphs intersect is where the system is solved. So I have set up a Desmos graph to kind of take a lot of this assessment in for us. To start out actually with the same situation as the previous example we saw where the mass of the first mass was 0.5 kilograms, the second mass was 1.5 kilograms. The first velocity was 1, the second velocity was negative 0.5, right? Going to the left at 0.5. And I have, so the purplish blue equation here represents the momentum conserved, solving for that final velocity of 1, like we had set up algebraically. The red equation satisfies the energy condition, so energy also being conserved. And where they intersect, so they actually intersect exactly on this graph here. What this shows is I will have a velocity of negative 1.25 going to the left, which we saw in the simulator. And then the x component, the 0.25, that's the final velocity of the second ball. That's the final velocity of the second ball. So that would be 0.25 going to the right. And where they intersect is going to be a perfectly elastic condition. If I were to turn down elasticity, I would see something that could fit along the purple line. It would still be along the purple line here because that's under the condition of momentum being conserved, but it would no longer be on the red line because that's only on the red line where these two intersect where energy also be conserved. Now, you might think there's only one spot where this happens. That's because of the initial conditions. If I change the initial conditions, like let's say the velocity of the first ball is now doubled, you see that my solution to the system changes based on where it is. So the Desmos graph, kind of the way I have it set up, shows us how the conditions of being perfectly elastic measure up.